Thank you for tuning in. In this video, I want to share a little bit of work I've been doing with the idea of VIO. Now, visual inertial odometry is a way to get position and orientation while indoors without a GPS signal. So in this video, I'm going to cover this documentation in more detail as well as the code associated with it. So I'll demonstrate my hardware setup as well as how to get this set up with a Jetson Nano and a T265. So if you're not aware, there's this great project by Auterion. It's the VIO project, but the documentation leaves a bit to be desired. So what I've gone ahead and done is forked this code and added some of my own comments, and I'll also cover this in detail in the video. But before I get started, let me give a quick demonstration of what we'll be working towards in this video. This is my HoverGames drone from NXP with their Pixhawk flight controller, and you'll notice that I'm flying currently in position mode. You can see QGroundControl down below. It shows I'm in the position flight mode, and it's maintaining position indoors relatively well. Now, this isn't going to be DJI quality, but you can still see that I'm giving no input, and with the T265, the Jetson Nano, the VIO package, that we're maintaining position really well. So here I'm beginning to yaw and just giving inputs while the aircraft is maintaining position and altitude, and what I'm going to do now is actually dive into the steps to get this up and running. On the hardware side of things, I can't stress enough the importance of making sure you have your data connection set up correctly. Otherwise, this is not going to work at all. So I'm going to cover this in detail just to make sure that you guys can successfully achieve this setup. So you'll see here that this is the 40-pin header on the Jetson Nano, and on the left I have the actual pinout from the Jetson Hack site. The 3 pins that we're most concerned with are ground, the UART transmit, and the UART receive. And you'll notice that the ground is the 3rd pin down. So if we were to count here, 1, 2, 3, this is the ground. Then we have TX and RX. And those go over to the telemetry 2 port on the NXP flight controller. Of course, this will work with any Pixhawk, but I wanted to use the telemetry 2. It's a 4-pin connector. We're using 3 of the 4, so I have the ground coming out to ground on this connector. I have the TX from the Jetson going to the RX on the NXP flight controller, and then we have the TX coming out of the flight controller to the RX on the Jetson Nano. You may be lucky enough to have a cable laying around that will allow you to make this telemetry connection, but in my case, I did not. So this is a little kit I've had laying around when I want to do some wiring with these JST GH connectors. Those are what a lot of the new Pixhawk hardware use for connections. And then on the other end, this DuPont connector, you have different sizes. Once again, we needed a 3-pin connector, very similar to a servo connector. And in this kit, you also have your cables. So on one end, you go into your DuPont, the other you go into the JST connectors. And that's what I use to make the connection from the flight controller to the Jetson Nano. Here is a top-down view of the setup. We have Jetson Nano with the cable connected to the flight controller, and then the T265 mounted, as well as power and this little Jetson Nano mount. So it's important that obviously you have it mounted properly, as well as the necessary power input. And I want to cover that in a bit more detail. In my setup, I'm using a buck converter similar to this. It steps down from 24 volts all the way down to 5, and this 5 amp one should be sufficient for your Jetson Nano. I'm running 4S LiPo, so 16 volts input to the power distribution board. So that connection is here. Those are soldered to the board. And then on the other end, this 5-volt output, I have a barrel connector. And that's what you see in this photo. Beneath, I have the buck converter mounted, soldered to the power distribution board. barrel connector on the other end with 5 volts going into the Jetson Nano. And just make sure, if you haven't worked with a Nano before, you do need to have this jumper connected so that you can run power from the barrel jack. And a lot of the testing I did from the wall, so I was able to plug in a standard power adapter for the Nano, 5 volts to test, and then was able to connect it to the buck converter and get power from my LiPo. Now, the other thing you may be wondering is how to mount this. There are different ways you can do that. What I used is a project from Bell. I was involved with the Bell Vertical Robotics Challenge. It's a very cool drone competition, so shout out to the Bell team. There's several 3D printable files in their repo, or these are the, we call them blocks that give you clearance above the flight controller. So you print 2 of these and then a mount to put your Jetson in. And once again, you can see that here. I have these zip tied to the frame and then the Jetson Nano mount zip tied to those blocks. And I'll put a link to this Bell VRC repo below. It's the 2021 phase 1 with these 3D prints, and you'll have all the STLs that you need to do that, or you can mount it however you want. But these make it super easy to get everything mounted and up and running. Let's cover one more thing as it relates to this hardware setup. Now, as part of the Bell Flight project, there's also the VRC phase 2. Once again, I'll put a link to this beneath the video, and in the 3D prints folder there's a T265 rail mount, and this is important because for my setup I have the T265 mounted to the rails of the drone. It's a common, drone frame with those carbon fiber rails. These slide on, and the T265's mounts just pointing straight forward. And last but not least, you'll need a Wi-Fi. Obviously, we want to be able to stream data from our setup to a ground station running QGroundControl. And so this is a Wi-Fi antenna mount. I have the Jetson Nano external antenna Wi-Fi mount. You can also use one of those USB ones for close range testing, but make sure that you have your Wi-Fi connection set up on your Nano, because that does not come out of the box. You'll need to add that, and then you'll be able to connect to QGroundControl over a Wi-Fi connection. I'm not going to cover the Jetson Nano setup in extensive detail, but I'll just give a quick overview because I want you guys to know that we're doing this from scratch. We're doing this from a fresh image that I downloaded from the NVIDIA site for Jetson Nano. I use Balena Etcher to create that image on the micro SD card. And then after that's done, we'll boot up. I had to use an external monitor to go through the setup process for Ubuntu. So set up the user account, then just allocate the full size of the SD card minus 16 gigabytes. You want to make sure that you have the max in setting. And then last but not least, once you are able to boot in to your Jetson Nano, make sure that it's on the network. You can see here that mine is connected. I now have the IP address, and once that is established, you're able to unplug and do everything over an SSH connection. So the rest of this video, the configuration I will be doing is with the Nano on my network, but from my Linux machine accessing the Jetson Nano remotely. In this section of the video, I'm going to cover in extensive detail the software dependencies necessary to get your VIO up and running. Now, I have created a fork of the Auterion VIO project. I've updated a lot of the README with stuff that I felt was missing and necessary for the setup. But if you want to skip this whole section, what I've done is created this gist, and you can go in here and sort of read at a very high level of what's going on. I have the different sections, and you can literally copy and paste these into your command line on your Nano and get everything up and running. And it's a bit of a shortcut for you to be able to move on to the configuration with QGroundControl. In the gist, I have a link to Automatic Addison. This is Addison Sears Collins. He does some of the best content, in my opinion, out there on ROS. And what we'll do is just run a couple of commands so that we can update our system and be able to install the ROS dependencies. So From this blog, I'm just going and entering these commands. I'm doing a system update, and that will allow apt to access the necessary repos to install the ROS packages. We'll go ahead and do a system update. And now that that's complete, we can install ROS. In Addison's post, he has the ROS Melodic desktop full version. You can see I'm just grabbing the desktop. We don't need the full install with a bunch of unnecessary packages. So I'm doing the base installation, and we'll go ahead and let that run. ROS has finished installing. What we'll do now is run a couple of commands to put the environment variables in our bash RC script, and we're going to source bash RC. What this will allow us to do is have these environment variables available to us. So I'll go ahead and just run this export and grep for any sort of ROS variables, and we should see them there. So everything is working as expected. And finally, for the ROS side of things, we're going to install some Python packages that will make our lives a lot easier when working with ROS. I forgot to mention we need to install the Python ROS dep package, so we'll go ahead and get that installed, and then we need to run a ROS dep init as well as a ROS dep update. ROS is now installed. The next step is to install the Realsense libraries. This will allow us to communicate with the T265. So I'm navigating through the repo just to show you guys where the installation instructions are for the Jetson Nano. So we'll scroll down, and similar to what we did with ROS, we have a couple of commands we need to run just so that the librealsense servers are added to our list of supported repositories. And then we can move on to installing the dependencies. The librealsense servers are added to our repositories, and let's go ahead and install librealsense 2 utils. We'll go ahead and let that finish up. And then we'll install the librealsense 2-dev package. When that's done, we'll be able to use a command called rs-enumerate-devices that will show us that our T265 is communicating. You might run into an issue where it's not. I encourage you to unplug it and plug it back in. I know that's a sad hack, but that's the way it is. So sometimes it doesn't pick it up immediately. You need to disconnect and reconnect it, and obviously make sure your entire system is powered. We'll move on to installing the Catkin tools. This is a Python package. If you're not familiar with ROS, Catkin is the build system, and these Catkin tools make it much easier to work with ROS workspaces as well as build them. I'll go ahead and run the Catkin command just to verify that it is in my path. We can see that it does respond, so that's good. The next thing I'll do is create a local workspace directory in my home directory called Catkin ws/src. That's where we're going to put the source code from this project. So I'll go ahead and cd into it, and I'm going to clone my repository. This is no different other than the documentation that I've provided. You could certainly use this or the Auterion, and I've gone ahead and cloned that. The code is now saved to my local machine. We'll move on to installing MAVROS. Since I have Melodic running on my Jetson Nano, I'll use the necessary packages. Make sure you use the packages appropriate for your version of ROS, and MAVROS will allow us to communicate with the flight controller through the Jetson Nano to our ground station. One of the things that the Auterion documentation was missing was this geographic lib installation. Now maybe they're assuming you already had it running, but I'm going to go ahead and just do a wget, download the script, and then run the install file. It'll install some geographic conversion libraries, but I had problems running this without this library, so I made sure to include it in the installation. Okay, guys, we're close on the software side of things. The last thing we'll need to do is build this code. And I went ahead and intentionally left this in here because I ran into a problem during the build, and I've added this both to my repository, my fork of the VIO project, as well as the gist. What you'll see is that as we build, we're going to run into an error, and that's because we're missing the ROS point cloud library. So you can see here that it says, could not find the package configuration file PCL ROS, and I was able to quickly overcome the build error by installing the PCL package. This is the point cloud library, which is necessary for VIO to work properly. After installing the point cloud library, we can build again, and you'll find that everything builds successfully, and we'll move on to the configuration of our flight controller. We've built the VIO project, and now we're going to do one configuration change so that we can connect to a QGroundControl wirelessly. Now I'm currently connected via USB connection. My flight controller is physically plugged into the laptop, and I have QGroundControl up and running. We'll change this parameter, and this will allow us to get telemetry over that telemetry cable to our Jetson Nano, and then forward to the ground station wirelessly over the Wi-Fi network. So I'm going to MAV0 config, and I'm going to disable this. We want to make sure that we have the other instance, the MAV1 config, set to TLM2. If you recall, that's the port that we created the cable for and plugged into. And the next thing that I'm going to do is go ahead and reboot so we can set our baud rate. When Pixhawk reboots, QGroundControl will detect the USB connection again. We'll go to parameters. We'll search for serial telemetry 2 baud. This parameter will set to 500,000. This baud rate matches what we'll be using in our launch file here in the next step. And this is all we need to do to now be able to communicate over the wireless network between the Linux laptop running QGroundControl and the drone running the Jetson Nano. I've gone ahead and rebooted my Nano and am going to SSH into it and cover what is one of the most important things beyond actually having your telemetry cable properly set up, but being able to see data. So I'm going to add my current user to the dial out group. This will allow us to see data coming in the serial port. Now I'm looking at dev TTY THS1, and that's where the flight controller is sending MAVLink to the Jetson Nano. So you'll see a bunch of gibberish, but that's good. That means we're getting data. And I want to CD into the project and show you guys the actual launch file. This launch file is important, and it'll show us the endpoints of where we're getting the data from the serial port, as well as sending it to the ground control station. Let's take a closer look at this launch file. I've exited out of the terminal. I'm going over here to the repo. This is the code that we've actually pulled onto the Jetson Nano. This is bridge mavros.launch, and lines 3 and 4 are the most important. Line 3 is what we just looked at, where we're seeing MAVLink raw data coming over this port. We have a baud rate here of 500,000. I've found that to work best. You will most likely not need to change this. If you did your telemetry cable setup similar to what I did, then that will be okay. But not line number 4, you'll need to modify this. In this case, once again, this code is running on Jetson Nano. This configuration is, and our ground control station, which is going to be my Linux laptop running QGroundControl. This is the IP address. You'll likely need to update that. But once you do that, you'll be able to launch, and what happens is that the flight controller is communicating to the Jetson Nano on this port, and then this is being forwarded to the ground control station at this IP address. After updating the launch file with the IP address, we'll give this a run. We need to source this setup.bash file that will allow us to access the project with ROS launch, PX4 Realsense bridge, and the bridge underscore MAVROS.launch. Now, I went ahead and left this in here. I ran into an error. I've covered this in the gist as well as the README. You'll be able to install it and not run into this problem, but we'll need the Realsense 2 camera package. So I'll run a sudo apt install Realsense 2 underscore camera. We'll get that up and running. We have the Realsense 2 camera package installed. Let's try this again. So I'm going to launch the PX4 Realsense bridge node using that launch file, and lo and behold, we're running. Now keep in mind my drone is powered up, my T265 is connected, the Nano's running. Obviously we're connected to it wirelessly. You see the Realsense node is up. The next thing I'll do is let me open a new tab. This is my desktop that I'm running a QGroundControl on, so I'm going to go ahead and launch it, and looky there, we have a connection wirelessly from Jetson Nano to the desktop, sending data into QGroundControl. Now, the next part of this tutorial, we're going to cover the parameters and vehicle setup to get this VIO working. I'll head over to the PX4 VIO documentation. Let me make a call out for this one configuration parameter. Now, we need to make sure that since our T265 is pointed forward, I've actually modified this setting in the bridge.launch file. This is the camera orientation. It's pointing forward, so I modified these parameters. There's a bit of an offset from the center of the flight controller, but take a look at those. You should be able to use those defaults and have this working successfully. We'll need to tweak a few EKF2 parameters. These are concerned with the external position information, which we're getting from the T265. I'll go to the EKF2 category and we'll see the EKF2 aid mask. I'll show the ones that I used. I'll just go ahead and click all of these and we'll end up with a bit mask of 344. So I'll go ahead and save that. We'll scroll down to the EKF2 height mode and we'll change this to vision. There are two other EKF2 parameters that I have not tuned. One is the EKF2 delay, EV delay, and then the others are the XYZ offsets from the frame. Since I specified those in the launch file, I think we should be okay. This does run well, so I'm not concerned with those at the moment. I'll go ahead and reboot the Pixhawk, and then we'll take a quick look just to verify that these EKF2 parameters have been persisted. So the first is the aid mask. You'll see it's 344. And then our other of height mode, we have that set to vision. We're done with the VIO params to get this running. Now, the last check we'll do is with the MAVLink inspector. Now, this is rather involved. I could do a whole video that talks about this, but I want to point out that you should be looking for this local position NED message coming through. That is certainly the difference between a standard setup and this VIO. And then for odometry, you want to look at the Q value, the quaternion value, W, X, Y, and Z. The documentation does go through what you need to do to verify this. Now, one thing that I will point out is this MAV ODOM LP message. It talks about needing to set this parameter to 1 so that you can see the odometry message coming through in the MAVLink inspector. In my case, that message comes through regardless of how the parameter is set. So I just wanted to make that call out. Perhaps the documentation is out of date. Perhaps I'm on a newer version of the firmware that's been updated. But in the MAVLink inspector, definitely confirm that you see odometry with the quaternion, do the check talked about in the documentation, and then make sure you have the local position NED message. I know we've covered a ton of information. This is, I promise, the last thing we'll do in QGroundControl is we'll set up our flight modes. In my scenario, I have stabilize as the default mode on the 3-position switch. The middle switch position I have set to altitude, and finally position. That's what we're most concerned about here. So We'll test these modes, make sure everything functions properly, and then be able to verify that we have great position hold indoors. I've powered up my drone. I've SSH'd into the Jetson Nano. I'm going to launch the node. We'll make sure everything comes up properly. We'll check that Realsense is running, and then we should be able to see data in QGroundControl. We'll be able to do a test flight, and I'll show that as well as the QGroundControl interface while we're doing position hold. After the flight modes have been configured, I'm taking off in stabilized mode. I'll put QGroundControl at the top of the screen just so you can see the flight modes as I switch, as well as my heads-up display and orientation. And I'll go ahead and switch into altitude mode. And what that will allow us to do if VIO is working correctly is to maintain altitude. So the left stick, you can see I'm not giving any input. The right stick, I can pitch and roll while the drone continues to maintain altitude indoors. Now I'll go ahead and toggle into position mode after altitude flight mode was well tested, and you can see just how nicely this is holding position. I was incredibly impressed for my first go. Now, actually, I'll be honest, this wasn't my first go. This is like my second or third, and I will mention that it's recommended not to toggle the flight modes while in the air, so do that on the ground if you're not comfortable. You know, switch to altitude, take off, land, switch to position, take off, test it out, and then land. But you can see here, once again, it's holding position well. Now I'm giving some yaw input just to see the effect, and you'll notice that it does tend to lose a little bit of altitude while I'm yawing. I'm only giving input on the left stick while the drone is maintaining position fairly well. So I've yawed right 90 degrees. Now I'll go ahead and continue the yaw rotation, bring it all the way down. You can sort of see here it's gaining altitude, and keep in mind that while this yaw is happening, the SLAM is running on the T265, so it's looking at me, it's seeing the light coming in from my window. You'll notice here that it's lost a little bit of altitude, but it's coming back up. Now what I'll do is go ahead and continue the yaw rotation, bring it all the way around to where it's pointing back to my garage door, and we'll see that in this case, you know, it's not looking out the window, it's not, you know, distracted by any light, and it continues to hold position well. But you will notice that there is a bit of vertical drift. The throttling up, it's gaining altitude, so I just gave a little bit of input and brought it back down. Now I'll toggle into stabilized mode. You can see that quick drop, so be careful. Once again, if you're doing this in the air, which it's not necessarily recommended to do so, you want to make sure you're prepared to handle that. Okay guys, I know I covered a tremendous amount in this video. Looking back, I probably should have broken this up into smaller videos, but I'm going to make sure that I share, once again, these links, and I'll put them in the description below. Be sure to look at them. This is the PX4 VIO documentation. I will be continuously updating my instructions associated with this video to be able to do this setup. And please just feel free, if you have a question, post it below. I'll likely follow up with some more specific videos, something a little bit shorter, centered around a subject related to this setup, but maybe not so all-inclusive. I know it was a bit overwhelming, but I appreciate you sticking with it. I hope that your VIO setup goes well, and don't hesitate to leave a question or comment below. And until next time, thanks for watching.